Hello, I'm Bill Pulanco with H.B. Fuller. I'll be presenting adhesive bleed-through in the hygiene market. Before I get into the presentation, I want to give a little information about my background. My current role at H.B. Fuller is Global Technical Service Manager. I'm responsible for developing our technical service teams globally, along with ensuring our customers receive standard world-class service. I've been with H.B. Fuller for 6 years. My background is in mechanical engineering. Prior to H.B. Fuller, I spent 10 years with a global diaper manufacturer. The first 5 years was in a plant as an asset engineer and project manager. My latter 5 years were spent in Southeast Asia ensuring the global engineering standards were followed for equipment design, installation, and startup. I have a total of 16 years in the hygiene industry. Now I'll get into the presentation. For the agenda, I'll speak about the current trends and impacts on bleed-through, and I think you'll be a little surprised at how the industry improvements have increased the risk for bleed-through. Then I'll talk about the details of bleed-through, which is an ambiguous term used to describe what H.B. Fuller has classified as 3 different issues: strike-through, migration, and exposed adhesive. Finally, I'll describe the best ways to prevent bleed-through. This issue can cause the manufacturers downtime and consumer complaints, and this can quickly turn into an expensive issue for manufacturers. It's critical that we understand bleed-through, the causes, and how to prevent it. For the key trends in the market, the first tier describes how developing regions have impacts on bleed-through. The industry as a whole has been bringing new technologies into developing countries that don't necessarily have the talent to deal with complex issues. As line speeds increase without factoring in the adhesive changes, shorter machine open times can become an issue with traditional adhesives that have longer open times. You can see this in the stacker and the bagger, where adhesive can build up due to the fact the adhesive has not set. The second tier refers to design improvements. Thinner diapers have reduced the vertical height of the substrates, which limit the amount of material that the adhesive has to bond to. The adhesive needs to move into the non-woven strands and make a mechanical bond, and if the vertical height is reduced, the risk for bleed-through increases. Also, the new softer substrates are made with raw materials that prohibit bonding. The typical response is to increase the coat weight, which leads to bleed-through. Finally, the third tier is talking about taking the cost out of the diaper. Cost reductions have lowered the basis weights of material, which not only have reduced the vertical height, it also has reduced the formation coverage, which is what we call exposed adhesive. There is also competition for shelf space. Compressing more diapers into a bag can promote adhesive bleed-through. While you probably think that the compression in a bag is not significant, the fact is end seal strengths do increase due to the bag compression, which is clearly demonstrating there is a significant amount of pressure to cause the adhesive to continue to make bonds. So these are key trends we are seeing in the market. They're not deal breakers. They just need to be factored into the equation when evaluating the different scenarios. I want to talk a little bit about the mechanisms that promote bond strength that can also lead to bleed-through. The purpose of an adhesive is to bond 2 substrates together. To make a good non-woven bond, the adhesive has to penetrate into the non-woven and actually mechanically anchor around the strands of the non-woven. The more the strands encapsulated by the adhesive, the better the bond. As mentioned before, the non-wovens are getting thinner and thinner. The reduced vertical height of the non-woven reduces the number of strands the adhesive has to bond with. Encapsulating strands too close to the surface of the non-woven can increase the risk for bleed-through. Bonding to the poly is done via surface attachment. The adhesive needs to wet out and actually get into the troughs and valleys of the adhesive to increase the surface area. In order to get good wet out, we need the adhesive with a relatively low viscosity. Low viscosity adhesives can move through porous materials like the non-woven and create bleed-through. It's a careful balance between enough and too much penetration that gives us good bonds without bleed-through. I teach my customers to make a good bond, we have 3 levers we can work with: time, temperature, pressure. If I increase my time, I can make a good bond. If I increase my temperature, I can make a good bond. If I increase my pressure, I can make a good bond. Unfortunately, these mechanisms to make good bonds can also lead to bleed-through. If you give me too much time, I'll bleed through. If you give me too much pressure, I'll bleed through. If you give me too much temperature, I'll bleed through. It's really a balance of these parameters that give us good bonds with no bleed-through. So I've talked a lot about bleed-through without giving a formal definition of what bleed-through is. As I mentioned before, bleed-through is an ubiquitous term that covers several different issues. H.B. Fuller defines bleed-through in 3 different categories. The first is strike-through, and this is seen on the machine as adhesive buildup. Second is migration. When seen at the end customer, the customer sees the product sticking together. And then the last is exposed adhesive, which is usually incorrectly identified and found online or at the customer. The first type of bleed-through is strike-through. Strike-through is when a force mechanically or pneumatically causes the adhesive to move through the substrate. This first picture is an example of a vacuum drum that has sucked the adhesive through the nonwoven. The adhesive is applied to the top of the nonwoven, but when subjected to the high vacuum of the drum, the adhesive is pulled through the nonwoven and transferred onto the drum. This can also be seen in vacuum conveyors and anywhere else vacuum is used. The second example of strike-through is caused by the applicator setup. High pattern air pressure, running the applicator too close to the web, high applicator back pressure can all cause the adhesive to be literally blown through the nonwoven. When blown through the nonwoven, the adhesive is now on both sides of the nonwoven, and any machine part that comes in contact with the nonwoven will typically build up with adhesive, which is seen in the picture here. And this is a snowball effect. The buildup will continue and eventually tear the substrate. Buildup can also be seen on dead plates, folding boards, and anywhere the equipment touches the nonwoven. This is also a good example of how untrained crews can easily create a significant amount of downtime. My last example for strike-through is on the rotary dies. Rotary dies are the best example of time, temperature, and pressure. Typically, embossing dies are heated to improve the bond strength along with pressure and time. If there's too much heat, pressure, and time in the embosser, the adhesive can be pushed through the nonwoven, which can be seen in this picture. The cutting die is also subjected to adhesive strike-through. The knife edge typically has to cut through adhesive, which over time can build up on the knife. Adhesive on the rotary cutting die can cause the product to flip out of the die versus transferring properly onto the exit conveyor. The typical solution for cutting dies is to use an oiler that applies a light film onto the edge of the knife. In my experience, if you didn't use an oiler on the die, it was difficult to keep the adhesive off of the knife edge. To summarize strike-through, it's seen as adhesive buildup on the manufacturing equipment. It's caused by the process forces that push the adhesive through the nonwoven. It can be caused by the vacuum, it can be caused by the applicator setup, or it can be caused by excessive pressure or temperature seen on nips, dies, and other equipment. This type of bleed-through is caused by improper equipment setup. Having properly trained technicians is critical to preventing this type of bleed-through. The second category of bleed-through is migration. Migration is how the adhesive flows or moves through the substrate after manufacturing. This is what most people assume is occurring when they see any type of bleed-through, and this type of bleed-through is seen typically in the final product quality. Products are typically stuck together in a bag. The first type of migration is excessive adhesive. As seen in the picture, the adhesive is too close to the surface of the upper and lower nonwovens. Obviously, too much adhesive has been applied and it can easily move to the exterior surfaces of the diaper. And typical sources of excessive adhesives are dripping nozzles or poor adhesive patterns. The issue with excessive adhesive is the fact that the nonwoven doesn't have the vertical height it needs to contain the adhesive. Any amount of pressure from being in a bag or in a roll can cause the adhesive to migrate through the nonwoven. The second example of migration is cold flow, and cold flow is the ability of the adhesive to move at room temperature. This picture is an exaggerated example of how a hot melt adhesive can move at room temperatures. This can was originally set up with the adhesive completely in the bottom. The can was then turned onto its side for a period of 24 hours. And over those 24 hours, the adhesive has cold flowed from the bottom to the side, all at room temperature. Cold flow can allow the adhesive to move through substrates with gravity as the only external force. But cold flow isn't always a bad thing. Cold flow is needed to bond difficult applications like hook and loop or specialty applications like core, where we want the adhesive to migrate into the troughs and valleys of those difficult to bond substrates, or we want the adhesive to migrate into the core to give better core stability. Cold flow can be controlled by the choice of adhesive raw materials, such as H.B. Fuller's crystallizing technology. This technology allows the adhesive to cold flow for a specific amount of time and then stop. The ability to control cold flow is critical to controlling bleed through. So the causes of migration: excessive adhesive and adhesive cold flow. Excessive adhesive coming from improper equipment settings and bonding issues, and then adhesive cold flow coming from the wrong choice of adhesive for the application. And remember, cold flow isn't a bad thing. It's only an issue when the cold flow is not controlled. The third type of bleed through is exposed adhesive. And when researching the different modes of bleed through, this was the one that was least understood. Exposed adhesive is when the adhesive is never covered by the substrates. Whether the substrates have holes that are intentional or not, the fact that the adhesive is not being covered is what causes this type of bleed through. The first example of exposed adhesive is on an apertured film. The apertured film has intentional holes to allow for fluid acquisition. If there is a tacky adhesive underneath one of these apertures, it will be felt through the film. Again, the type of adhesive, the choice of application can improve the issue with exposed adhesive on apertured films. The second example of exposed adhesive is of a non-woven with unintentional openings that cause exposed adhesive. In the picture, you can see there's been a hole ripped into a poly. There's a non-woven covering this poly, and there's an adhesive bead line that goes through. Where the adhesive is not covered by the non-woven strands, the adhesive is bonded to another article, whether it be a diaper or another layer in a roll. And this has made a bond, and when they were pulled apart, it's actually ripped a hole in the poly. Formation of the web is critical to protecting the adhesive from unintentional bonding. As I mentioned, substrate formation is critical to preventing exposed adhesive. Here's an example of a 23 GSM spun bond. And both of these pictures are taken from the exact same piece of material. The left-hand side is a highly condensed area of the web where the fibers are very close together, which would prevent any kind of exposed adhesive. On the right-hand side, on the other hand, there's very large open areas. The fibers are very far apart, and the density is much less. Not enough fibers to cover the adhesive is one of the types of exposed adhesive. In summary, exposed adhesives can be caused by apertured substrates where the holes are intentionally placed into the substrates, or they can be caused by nonwovens with poor formation, which leads to open areas in the nonwoven exposing the adhesive. So we've talked a lot about bleed through. We've defined it, showed different areas where it shows up in the articles, but the real question is, how do you prevent bleed through? While it's common to focus on the adhesives, there is no silver bullet that can fix every issue. Having suppliers that are experts in their field is critical to resolving any manufacturing issues, including bleed through. Involve your suppliers early in the process. Any changes to process, raw materials, or new R&D projects should be a collaboration with you and your supplier early in the project. The answer to solving bleed through is the collaboration of you and your equipment OEMs, both adhesive equipment and diaper machines. The answer to solving adhesive bleed through is a collaboration with you and your raw material suppliers, both adhesive and substrates. So how does H.B. Fuller prevent adhesive bleed through? H.B. Fuller has a proactive and methodical approach to best match the correct adhesive for the customer-specific application. First, we evaluate the customer's product needs, bonding requirements, substrates, and then the equipment processes. Then, using our in-house coding capabilities, we run a lab demonstration to help our customers make a data-driven decision on how best to optimize the adhesive performance and build confidence before they make any changes to their line. Once the adhesive is proven in the lab, then we go and run a commercial demonstration on the customer lines to validate the adhesive performance as demonstrated. And finally, we support the final conversion, whether it's for an adhesive actual change or for a substrate change or any kind of product changes. And all of this is supported by H.B. Fuller engineers. The previous slide mentioned in-house coding capabilities. H.B. Fuller has technical centers that have both coding and analytical capabilities globally to support our customer needs. These coaters use the latest technology that can run up to 1,000 meters per minute, which is approximately 3,200 feet per minute, and the high-speed design was intentionally done to match the current and future needs of our customers. We can run multiple applicators with multiple adhesives simultaneously to best mimic our customer processes. We can make tri-laminates with combinations of construction and elastic adhesives or two construction adhesives. We also use the coater to support substrate changes, do product changes, or any other process changes that may affect the adhesive performance. Recently, I got a call from a customer saying that they had changed their nonwoven and now the adhesive didn't bond. Well, we used our lab coater with their nonwovens and the adhesive to show that the adhesive actually did bond to the nonwoven, and we were able to discover the root cause was actually a process issue, not a adhesive bonding issue. Our analytical capabilities are used to help identify not only just the potential bleed-through issues, but we can also test adhesive performance. We have H.B. Fuller standard test methods we can use for this. We can use customer-specific test methods, or we can develop new test methods if an application has never been run before. The use of H.B. Fuller Technical Centers is actually a huge benefit to our customers. Here's an illustration to show the benefit of using the technical center versus a production line demonstration. Production demonstrations take a lot of downtime to drain the tanks, they waste a lot of raw materials, and they're a significant cost to our customers. Using an H.B. Fuller Technical Center, it literally is just the cost of a couple of rolls of raw material. In summary, when bleed-through occurs, there is no one solution. As I've shown, there are several ways bleed-through can occur. If you look at the problem from a single point of view, you may miss the root cause. Equipment settings influence bleed-through. Raw materials, adhesive and substrates influence bleed-through. Most importantly, selection of your supplier and making sure that they have experts in their field, as well as collaboration with your suppliers. I have a philosophy that if you know the root cause, then you will know the solution. What I've presented are the root causes of bleed-through. Now it takes the collaboration of all the participants, diaper manufacturers, OEMs, and the raw material suppliers to identify and correct early in the process any potential bleed-through issues.